So there was an interesting video on the Kotlin subreddit the other day about handling a particular interview problem, and I wanted to kind of show how I would probably approach this problem. So the problem that they were covering was, imagine that you have um, a word rectangle that looks like this, and this is there are words you can construct by kind of snaking through the various words here. And you can see there's the word Kotlin. If you go start at the top left and then go right to down to and then over one, and um, you're given a list of words that may be that may be in this list, that may be in this rectangle. You have to determine which ones are actually present. So this is the dictionary that you're given, and obviously it could be a lot bigger than this, but for this example, um, this is all, and you can see a few of these like line is here, and I think most of these words in this example are actually here. So the goal is to iterate through letter by letter and kind of recursively explore the neighbors and kind of do this breadth first search kind of. It's not exactly a breadth first search. It's a, because it's a small enough search space, it really is just a depth first search. So the first thing that we want to do is we want to normalize. We want to turn this dictionary into a set. You can see it's comma delimited, and we want to normalize it. And you can see that the letters in the rectangle are all capital, so that's something that we need to deal with. So we need to do a couple things. We need to split, and everything happens to be exactly split by comma space, and then we need to map to uppercase, and finally we want to convert it to a set. So I know this is, in the context of an interview question, this might be fine, but this actually creates a list. This creates a list, then it can convert to a set. This is really easy to, if it's easy to fix, you might as well do it. Split to sequence here, it creates a sequence, and now map is returning a sequence instead of a list, and now there's only one collection that's created at the end. So now this is a reasonably efficient representation. So the next thing that we're going to do is we're going to kind of create a class for representing what we're going to do. We're going to call this class a WordRectangle. And we're going to pass it the input data. And this will be kind of apparent why we want to do this in a moment. So we have this data. The data is the original word rectangle, but it's not in a very accessible format. It's just kind of one big string with some new lines in the middle of it. With trim indent, it essentially looks like this when you actually read it in, but it's a little bit easier to read when it's indented like this. So the first thing we want to do is kind of fix that. So we want to say something like this. And again, you can say split to sequence to fix those new lines. And just in case, this is, probably overkill, but I just want to double check that this is actually normalized to the uppercase and trimmed. And so now, just to make sure, we can print what this looks like. So we're expecting a list with 3 elements in it. Okay, there we go. That's what we want. So let's start working on the thing that we're actually trying to do here. So we're going to create a find strings function, and this isn't going to do everything that we're looking for. We just want to say, hey, starting from this first letter, can we, or any arbitrary position, can we find this word? And actually, there's a couple different ways. Like, are we actually looking for that word, and you know, or are we looking for all possible words, all possible strings that are of a particular length? So it'll be apparent why we do that in a little bit. But so for now, let's start out with this interface, this method signature. So this is saying, starting at a given point, like 0, 0, find all words that are of length 5, for example. So this first word is, or sorry, 6. This first word is length 6. So we're going to find all words of length 6 from here and check to see whether each of these words is in that list or not. So first of all, if you have an empty string, so I mean, you know what, let's not worry about that for now. So we can say the letter at the position is the one that we care about. So if we ever ask for something that's out of bounds, if the index is out of bounds of the list, if it's negative or off the end, then return null. And so we do that twice here. And so if at any point we ever are given an x and y that's out of bounds, then we'll just have a null here. And if that happens, well, the point of this method is to return the set of all strings that's reachable from this coordinate. If its coordinate is just out of bounds, then we don't even care. It's not really valid. So we're just going to return empty. So this is kind of one base case. Then another case is if we have a string of length 1, then and you're saying like, well, what are all the strings reachable from this top left corner that is of length 1? Well, it's always just going to be whatever character is at that location. So we can just say something like this. So okay, so now we're assuming for now that the length is greater than 1, and that means we want to find k plus all of its neighbors. If length is 2, then it's k plus everything reachable from that space. And as in the other video, we want a notion of we can just kind of have a list of directions. If you're looking at the letter U, then you want to go up, left, right, and down, and that's kind of x negative 1, x positive 1, y negative 1, y positive 1. And a good place to put this is in a companion object. You don't have to make your companion object private if it contains private things, but it's a little bit cleaner, because then if you have a public companion object with private things in it, other classes can still see that there's a companion object. There's just nothing that's public. So if the only thing you're going to put as public is private things, you might as well just make it private. So those directions are like so, and so we can just do we can do a list of pairs, because a pair is just 2 things. And if this were a real program, I'd probably recommend using like a point class or some other little data class to like more correctly, more semantically describe this data. But if you're being kind of scrappy, this is fine. So this is one direction. This is the like left 1 and right 1, and then here's up 1 and down 1. So these are like x offsets and y offsets. So what we want to do is, so what we're doing here is this recursive algorithm where if we're trying to find all strings of length 1, it's just that character. If all strings of length 2 reachable from a particular coordinate, it's that character plus all the neighbors called recursively with one shorter length. So if it's 3, then it's k, from k with 3 to O and N with 2 back to k, a, u, or t with one length remaining. And then that's kind of the end of it, and you kind of recursively fold that back up to the top. So now we're going to iterate through each direction as a sequence, and each if you do map here, you can see it takes these pairs, and I'm going to call them x2 and y2. So remember that we were planning on calling this recursively. So we say find strings, and we're gonna decrement by 1. And this is almost what we want, but remember that we aren't just traversing into our neighbors. We're actually taking whatever they return and prefixing it with the character that we have here. So we can just say and so this is the string. This is all the strings returned by the subclass. Sorry, the subsequent calls here, and we just say something like this. So this is almost what we want, except if the error here is that it's not a set. It's a sequence of lists of strings, and so if we call toSet, then now it's a set of list of strings. And anytime you see this, you're like, oh, there's an extra layer of collection, and you want to kind of flatten this list out. Well, that means you need to call flatMap. FlatMap will, whatever iterable thing you return from it, it will, flatten those out automatically for you. And actually, we can do one better than that, because we're already iterating over directions here as a sequence anyway. If we just call this as a sequence, then there will be no find strings will still return a set, but other than that, there will be no additional collections allocated. And it's not great that map here is creating another, it's allocating kind of a lot of strings potentially, but I think in the grand scheme of things, it's not too bad. So there's one other little edge case that we have to worry about, is length being less than 1. If it's just one of those things where if you have something like this in your dictionary, it should still work. So what we want to say is this, return empty set. So it's kind of a weird condition, but if we're ever in this situation, just abort. So now we have if we're out of bounds, return empty set. If length is less than 1, return empty set. If length is 1, this is kind of our main happy base case, because eventually all the traversals get down to 1, and then we stop and kind of return the one character that we found there. And finally, then we actually start returning things. So if we create a rectangle here, we want to see, what does this actually do? Does this actually work? So we can say rectangle.findStrings. Well, that's not how this works, remember. So we want like 0, 0, we want to find all strings of this length. And you can see it actually does, it like ping pongs back and forth, because that's one possibility. KO, KO, KO. And if you just kind of scroll around, you know, there's the word. So we know it's in there. So let's, what we want, what we're really trying to do is something like is the word Kotlin in this collection. And of course, I mean, it was just there. We just saw it. So yeah, so we know this is true. So now what we want to do is iterate through each position and each word to say, hey, is this word there or not? Is this word in this rectangle somewhere? So the way we can do this is, remember we're trying to do this, basically programmatically. We're across the entire dictionary. So we want to iterate through every coordinate in this rectangle, and we don't really have a good way to do that right now. And but lines, if you look at lines is a list of strings, and so the length of the list is the height of the thing, and the length of an individual string is the width of the thing, or the x dimension. And we're gonna assume that this is like an actual rectangle right now, and not a jagged array, something like this, because that's out of scope. So really we want something like something like this. Well, not y, obviously. But these are in lines. Lines is private. We could make lines public, but that's kind of gross. Let's not do that. So the easiest way to do this is we can say we can generate a new getter that is derived from lines. And this could even just be a val, but this makes it a little bit more stateless, I guess. So this returns all the indices and that's a nice thing that we can iterate over here. It avoids some kind of like a more out of bounds problems than we wrote this to be resilient out of bounds, but why do that on purpose? So there's that, and assuming that our lines is not empty, we can just say something like this. And if we want to be paranoid, we could I don't know, getter null 0, I don't know, whatever. At some point it's kind of overkill, and you're like, well, what's in scope for the problem? And you're like, well, let's assume that the word rectangle is not empty for now. Anyway, it's probably because I don't know exactly how to create an empty int range offhand. Yeah, okay, fine. That's not too hard. Okay, so now we're iterating through here, and if we want to make sure that this looks right, so we're expecting this to print x up to 3 because it's 0 indexed, and y up to 2. So let's run this real quick. So x goes up to 3, y goes up to 2. Okay, so that's what we expect. And so now the next thing we want to do is for each word in the dictionary, if word in rectangle dot find strings x y word dot length. This is exactly what I was doing here. Then say something like this. So we expect this to work, and so now we can see we found Kotlin starting at 0, 0, line starting at x equals 2, y equals 1, and fun. Yeah, fun starting here. So it seems to be working, but one thing that you may notice is that this is probably not super performant because for every single cell, it's repeating this entire find strings here. And on top of that, some of these things are the same length. So find strings for for a coordinate and a word of the particular length is exactly, we're doing the exact same call multiple times, which is obviously not great. So let's measure first how bad this is. There's an easy way you can do this in Kotlin, just using one of these measured time blocks here. Some of these are experimental. I think this one is fine. I'd rather not use those in the scope of this. We don't need it. So then you can say, this operation took this long. So I don't think, keep in mind this is on a laptop, and those kind of have CPU scaling stuff. So it's not going to be super consistent. But if we look at, so it takes 20 milliseconds. I mean, that's not bad. Let's make this a little bit more complex to kind of stress test the system a little bit. I'm just, making it bigger. So, okay, now it's taking 240 milliseconds. And, if you do it a little bit longer, I mean, it's almost twice. So there's some like JIT compilation, so it's almost twice as fast. Or it's a little bit more than twice as fast. Sorry, half as slow. It's not taking quite twice as long, is I guess my point, because Java is doing its thing. So one of the things that's pretty interesting about this problem that you may not realize at first is this is actually a dynamic programming problem. So if you're looking at this, this is kind of like what the grid is like, and you're so you've got these things here, and when you're starting out here at the very beginning, like we were talking about, we had this 5, and then so we're starting out the kind of, if you're visualizing the arguments here, we're at 0, 0, 5 length, and then it navigates to the neighbors, then navigates to those neighbors, and then back again, and so on. So my point here is, when you're at this k here, when you're at the first cell, the list of words of length 5 that are reachable from k from this first cell are always going to be the same. And we're also calculating the list of words of length 3 from this cell that are reachable from this cell, and that's always going to be the same. And same for all of these. So after you've calculated the the list of strings of length 5 for the first cell, you will have also ended up calculating the length for all these other ones. Sorry, you'll end up calculating the list of words for each of these other cells. So if later on you're looking for a 4-letter word starting from this cell, you'll actually already have calculated that once while processing k. And so what makes this dynamic programming is that there's a list of subproblems here, and they overlap a lot, because in processing the first problem, you partially processed all these other problems too. And dynamic programming is really, to me, kind of a fancy way of saying like memoization of subproblems. And memoization itself is also kind of a fancy form of caching. Not even that fancy. So if we go back to our code here, let's see if we can add some memoization to get this time down. So memoization in this case is just take all these arguments, and if we've seen them before, return what we saw before. And this is pretty easy. So let's go ahead and do that real quick. And it's going to be a mutable map because we're going to be modifying it. And normally, if this were production code, I would create a data class that encapsulated all of these. It implements equals and hash code and all that. But if you're being scrappy and you don't want to create another class, you can just use a triple. This is another thing that Kotlin provides, and it has no semantic meaning, which is a kind of a bummer. But there isn't really a lot of semantic meaning to begin with, so I think it's fine. And we're going to map it to a list of our set of strings here, which is our return value. So what we want to do is, so remember what we're doing. If we've seen these arguments before, return the set again. And if we haven't, then after we've calculated it, save it in the cache, and then next time it'll be faster. So let's just kind of create our key here. And we can say, let's look it up in the cache. And if it's present, now it is the thing that is in the cache. We can actually just say return it. And so this is a nice little one-liner that's good for this kind of thing. So now if you run it, it still works. It seems to take a little bit longer. I think that's just a coincidence. Or longer, whatever. It's not running faster, that's for sure. Well, it's because we haven't actually finished it yet. We're not storing anything in the cache. So the last thing we want to do is, like, right before we return, we actually want to stuff it in the cache, and then then we'll be done. So also is great for this. It takes the takes the return type, the return data, as an argument, and then passes the original thing through. It doesn't change. You can't change the return value from also. It's whatever it's being called on gets returned. So obviously, we're using the same key because that makes sense, because we already have it. We've already calculated it once. We're just going to use it again, and it is the value of this, the thing we were going to return before. So now if we run it again, now it's taking now it's a lot faster. So this is also kind of a requirement for the way this code was set up here. Notice that we're calling this a lot. We could do some kind of caching on this side, but this is a nicer design because this way it's all self-contained inside this class. And so that's it. I think hopefully dynamic programming to me doesn't seem to come up that often in real code, but occasionally it does, and it's cool to recognize when if there's some sub-problems and you've got kind of pure functions. There's no side effects. It's just mapping from an input along with this to an output. Then that makes for super cacheable, super memoizable results. It does trade off memory for speed, but if you think about it, the first time you call this with a word of length 5, it has to go through the calculation, and it's kind of expensive to kind of traverse down through this string. But then every other time that you try to call it, it's in the cache. So with a sufficiently large dictionary, the amortized time of these lookups goes down to a constant time. So even though the worst case is not great, but if you're calling if you're checking multiple words of the same length, and words don't vary that much in length, if whatever dictionary they have is probably going to have less than 10 letters anyway per word. So chances are after a few words everything's going to be cached anyway, and then you really get this nice amortized time complexity. Obviously space is a little bit different, but yeah. So hopefully this was useful, and just let me know, leave a comment. Thanks.